Hey, everybody. So we're going to talk about, in this video, we're going to introduce the idea of the inverse trig functions. And I want to start with just a little review of inverse functions in general, okay? So what is an inverse function? Well, an inverse function, without being very technical, we can say it is a function that, if you have an original function, the inverse function, and I'll give the notation in just a second, undoes the original function. Right? So what I mean by that is if I have a function f of x, if I have the input a leads me to the output b, then the inverse function, and the notation is this, an f with a little -1 exponent. It does not mean 1 over, okay? It's a different use of the exponents. This is f inverse of b equals a, right? So if I put a into f and out comes b, I put b into the inverse and out comes a, right? So for example, if f of x was the function that took a number and multiplied it by 3 and then subtracted 2 from it, then the inverse function would be the function that took a number, added 2 to it, and then divided the whole thing by 3. So let's do an example. If I took f of, let's take f of 2, we get 3 times 2 minus 2 equals 6 minus 2, or 4. So f inverse of 4, I get 4 plus 2 over 3. That's 6 over 3 equals 2, right? So in the original function, I put in 2, out came 4. In the inverse, in went 4, out came 2, okay? So that's what an inverse does, all right? So let's look at something a little bit trickier. Suppose I have the function f of x, let's use g of x. G of x is equal to x squared, and I want the inverse function. And so a good idea might be the square root, right? It undoes squaring a number. However, there's a problem. Notice that g of 3 equals 9, and g of -3 also equals 9, right? Both of those numbers, when you square them, you get 9. So what should g inverse of 9 be, right? Do we give it 3 or do we give it -3? It's the inverse function, okay? Well, this square root that I've written, we've chosen the positive square root, okay? But this was a choice. And graphically, what we're doing here is something called restricting the domain. When we have this kind of problem, we have a function and we want it to have an inverse, but it has this issue where it's not clear where the inverse should go to, meaning there are two possibilities. Here we had two possibilities. If we look at the graph of the square root, or the square function, we get a parabola, right? So it's not perfect, but imagine that's a perfect little parabola. And the problem was that if we had an output of 9, for example, here we have -9, -3. Let me erase that, make it nice. On this graph, there are 2 points that represent an output of 9, -3, 9, and 3, 9. And our inverse function, which goes backwards, looked at the input 9 and didn't know which one of these to look at. And we made a choice. We said, you know what? When we do this inverse of the square function, we'll take the positive square root and we'll look just at this side. We've decided to restrict the domain. We're assuming that the original function didn't have this domain that was too large to actually give it an inverse. For a function to have an inverse, it has to be what we call 1-to-1, that that we always have with functions. Each input leads to only one output. When it's 1-to-1, each output can only have a result from one input. In the square function, this isn't possible unless we restrict the domain. And so we take the inverse to be the positive square root. If we need this negatives for something, we can also choose that, but it's a choice we make. So let's think of that in terms now of our trig functions. Start by looking at cosine. We want, so given the cosine function, let's say I have cosine of some angle is equal to some number b. What I want is the inverse cosine, sometimes called the arc cosine. What we want is the output to be A, the angle from over there, right? So when we're looking at it this way, we have our angle, and then the output is a number. Of course, we know the number corresponds to the coordinate point on the unit circle with our whole setup for cosine. But with our cosine, we're putting in a number, and we find the angle that led us to that number. That's what the inverse does. So it's like we're giving the coordinate on that circle and saying, what angle would have this coordinate? There is an alternative notation for this, similar to the one I used above, where we would write inverse cosine with this little -1x put in. This is some of the worst notation in mathematics. Mathematics is usually really good about notation, but when we write cosine squared, as we've seen, right? When we write cosine squared of x, we mean cosine, we mean this. When we write cosine inverse of x, or inverse cosine of x, we do not mean this, right? That would be 1 over cosine or secant on the right-hand side. It just means the inverse function of cosine. That's what that -1 means, or arc cosine, okay? Now, here's an interesting question we might ask ourselves. I told you when we put in a value for cosine, a number into arc cosine, it returns the angle that would have that cosine, okay? So for instance, if I put in cosine, let's do arc cosine of 1/2, the thing that comes out should be the angle that has a cosine. We're looking for some theta that has a cosine of 1/2. That's what's supposed to come out of this. If we go to our unit circle, let's draw a quick unit circle and try to recall some of the values on it. So let's go with green. So you might recall, so here's my angle in standard position. So it's got its initial side on the positive x-axis. We want a cosine of 1/2, something about, that looks a little too small, but if you look at the unit circle, there's an angle right here, about right here, and this is the angle pi/3. Right? And it's true, cosine of pi/3 is equal to 1/2, and so pi/3 is a good candidate for what we put for theta there. There's a big problem though. The big problem is there's another angle, this angle there that goes all the way around. It's true that cosine of, so we've got to go an extra 2 pi or 7 7/3 pi. So 2 pi around plus the original third, we get 7 pi/3. This also is equal to 1/2. There's also an angle down here, negative pi/3. That has coordinates 1/2 negative √3/2, and cosine of negative pi/3 is also 1/2. And then of course we could wrap all the way around this way. We can go around 1,000 times and keep ending up at one of these two angles. So we have these two we have an infinite supply of coterminal angles to these first two angles I wrote down that all have a cosine of 1/2, which means the inverse doesn't know which one to choose, right? And the inverse is a function, and so that for the input 1/2, there should be just one angle it spits out, and so we have to make a choice, just like we made with x squared and choosing the positive square root when we had a choice. So let's look at this in our cosine graph. Let's first illustrate the problem. Oops, that was the wrong thing. I want this. Here's a line. This is at 1/2. Each place where this orange line intersects the cosine graph is a place where the output, where the cosine of some angle is 1/2, right? I can do this forever, right? If I keep zooming out, we're going to see more and more places. You'll see the ones that I came up with as we were doing this, and we can keep going forever. And so we have to decide, whoops, which one to choose. And here's the choice we make. We're going to just look at one piece of the cosine graph, and it's going to be the piece between 0 and pi, right? So notice this part that's now, maybe, oh, that's as bold as it gets. This part of the graph that's between 0 and pi, inverse cosine won't just give us an angle that has, so let's go back to our example. When we asked for the arc cosine of 1/2, we weren't saying what angle has a cosine of 1/2. We were saying what angle has a cosine of 1/2 and is between 0 and pi. Okay, that's the choice for the inverse cosine. The angle it gives us will be the one between 0 and pi. And so in this case, that's pi/3. Right? And there's only one here. If you look at where this line intersects, oops, there's only one intersection point in the section of the graph that I have in black, right? And so in that section, there's no ambiguity. The inverse cosine knows exactly which one to choose. In our unit circle, if we're thinking about it in that way, what it means, it will choose the angle, right, somewhere between 0 to pi in the positive direction. So in this case, again, it's this first pi/3, right? Once we go all the way around, we're bigger than that. Or if we go in the negative direction, we're outside of that. And so we're only looking on the top half of the unit circle in the positive direction that first time around. Okay, and so that gives us our inverse cosine. It gives us a way to make that decision. Okay, we do a similar thing with sine and tangent. So let's look at sine. Notice we would have the same problem if I had some value I was looking for. We have all these intersection points. So we're only going to look at one section of sine. The section we choose to look at, let's make this a little bigger, is between negative pi/2 and pi/2. It's a different section than cosine. Notice in both cases, we're choosing something where we go all the way from the top to the bottom or from the bottom to the top, right? So we can get every possible value of sine. Remember, sine's always between -1 and 1. And so here we're at -1 when we're at negative pi/2 up to 1 at pi/2. So inverse sine or arc sine only looks for angles between negative pi/2 and pi/2. And then tangent, we have the same problem, right? There's all these places where tangent hits all these values. We choose, again, in this case, is between negative pi/2 and pi/2. So we only look at this one strip of tangent in the middle when we talk about the inverse tangent, right? So when we ask questions about inverse tangent, I say, what angle has a tangent, so inverse tangent of 1, I'm asking what angle has a tangent of 1, and that's going to be pi over 4, because that's the one between negative pi over 2 and pi over 2. So let me summarize all that. So what we have 3 inverse functions: arc cosine of x, or also written cosine inverse of x. And the domain, well, remember what we're doing. We're putting in the outputs of cosine, and the outputs of cosine are always between -1 and 1. So the only inputs that make sense are -1 to 1. And the range, it's going to output angles, and it's always going to output angles between 0 and pi. Okay. And then we'll have arc sine, or sine inverse of x. The domain is the same, -1 to 1. The range is a little different. We made a different choice. It's looking for angles between negative pi over 2 and pi over 2. And then arc tan, or tangent inverse, is going to have, now this one's a little bit different. Remember, the domain of the inverse tangent comes from the range of tangent, and tangent, as you can see on the graph that's still up, its range is infinite. It goes from negative infinity to positive infinity, or all real numbers. So you can put any real number into tangent, arc tangent, and the range is almost the same as arc sine, except we can't include the endpoints, right? Because remember, the range of arctan, or inverse tangent, is the domain of tangent. That's a relationship between functions and their inverses, and these are not in the domain of tangent. It has asymptotes at these values, and so this is the picture we get. Let's do one last thing before we go. Actually, 2 more things. First, let's take a look at the graphs of the inverse functions. When we graph the inverse functions, they are flipped over the line y equals x. So I'll put, there's the line y equals x. Let's square this so it's more recognizable. So here's the inverse tangent. It's a reflection of that. So the red one is inverse tangent of that. It's the reflection of the tangent graph over the line y equals x. Let's look at cosine. So here's the little piece of cosine that we choose when we want to make our inverse. This is the restricted domain, and the inverse is reflected over that line y equals x. And then finally, let's look at the sine. There's the little piece of sine between negative pi over 2 and pi over 2 that our inverse is concerned with. And there's the inverse graph. We don't use the graphs of the inverse all too often, although inverse tangent has some good uses. But what we often will use these inverses for, among other things, is to solve certain kinds of problems. And we'll end this video. We're going to do more stuff with these, but let's end this video with a quick example, just the tip of the iceberg of how we can start using these things. Let's suppose, let's suppose, for instance, we knew that we had maybe, I don't know, we're standing 25 feet away from some pole that we happen to know is 15 feet tall. And we were curious what the angle from our angle of elevation as we look, or the angle of elevation from our feet up to the top of that pole, right? Maybe we were setting up a camera or a light to light a flag at the top of that pole. That's a good excuse for why we would want to do this. And so we want to know what this angle is. Well, what we know is that the tangent of whatever theta is, remember we have these, the triangle definitions of our sine, cosine, and tangent is opposite over adjacent. So this will be 15 over 25 or 3/5. All right, let me just write this clearly again. Tangent of theta we know is 3/5. We can find what theta is by taking the inverse tangent of both sides. And we'll get that theta is going to be the inverse tangent of 3/5. All right, undoes that tangent function. Okay, so let's just go ahead and I'll use does most since it's open. We've got a nice, we've got a collection of functions. You see this inverse tangent or tangent to the -1. I mean, it is inverse tangent is how we should say it, but it looks like an exponent. And I want the inverse tangent of 3/5. We get about, theta is about 0.54 radians. They might have a degree mode in here. We can convert by multiplying by 180 and dividing by pi. So this is in degrees, approximately, let's just call it 31 degrees. Okay. So that's a really basic way that we can use our inverse functions. Also notice that that 0.54 radians is in the range of tangent, -pi/2 to pi/2, right? Half of pi is about 1.5. So somewhere between -1.5 and 1.5-ish. This certainly falls in that range. All right, we'll do a whole bunch more with these in later videos. This is good for now. Thanks, everybody. I will see you next time.